Hello there! In this tutorial, we are going to be talking about collisions in Pygame. And specifically, we are going to create a project you can see on the screen right now. And the really important thing I'm going to cover in this tutorial are the collisions between moving and static objects, as well as the collisions between two moving objects, which can be quite a hassle if you don't know how to think about it. So this is what I'm really going to focus on in this tutorial. And understanding the logic behind collisions is fundamental to make more complex games. Like a Zelda or Mario game that I created on this channel, they both use collision mechanics quite extensively. And there isn't really that much else to talk about, so let's jump straight in. And the first thing, just to save some time, I have already created a basic project. So for this section, I want to talk about the project setup, and once we have that, I'll talk about collision logic. But let's have a look on the code, what we already have. So here we have the project already. It's not the shortest thing ever. We have nearly 150 lines of code, but it really isn't that bad. I'll explain all of this in just a second. But if I run this project so far, here is the project you have seen in the intro, except we don't have any collisions. So the blue rectangle here is my player. I can move it around and nothing happens. And in the same logic, the red square is supposed to be a ball that moves around. Right now, it's just static without any collisions. So we can move around, but we can't really do anything other than that. And well, we are going to add collisions in just a bit. But let's first talk through this entire project. Now, all the way at the top, we are importing pygame, sys, and time. Pygame and sys are the basic things you need for pygame. And time is going to be used for delta time that we're using down here to make the entire project frame rate independent. If you don't know what that means, check out this video. In fact, if you're new to Pygame and you feel all of this is too complex, check out this video. It's explaining the entire module in quite some detail. And I will assume that you already know basic Pygame. After the import, we have 5 classes. We have static obstacle, moving vertical obstacle, moving horizontal obstacle, player, and ball. And I'm not going to go over them for now, just assume they do what the name implies. I will explain them in just a second. For now, just assume they work. Now, once we have that, we have a general setup with pygame.init, and we are creating a display surface. Nothing complicated so far. Then we have a group setup. And in here, we have all sprites and collision sprites. And all sprites is for literally every single sprite we are going to create. And this one is going to draw and update every single sprite. Collision sprites are for all the obstacles that the player is supposed to be able to collide with. Or well, the player and the ball. So this group here is literally just to figure out which sprites are supposed to be collided with and which ones aren't. It doesn't really do anything besides that. And once we have the groups, we can create some sprites. And in here, we have 7 sprites in total. We first create 3 static obstacles. And really, all we are doing in here, we are creating a position, a size, and then which groups this sprite is going to be in. So all of the static obstacles are in all sprites and in collision sprites. After that, we have our moving obstacles, and they work in the same way. We have a position, we have a size, and then we have some groups. And the arguments here are identical compared to the static obstacles. So all of this is ultimately fairly simple code. And at the end of all of this, we have our player and we have the ball. And those get predefined positions and sizes. So all they need is all sprites to place both of them inside of this group here. And once we have that, we actually get to the game loop, and this one is very simple for this project. At the beginning, we're getting delta time, and we're using delta time in all sprites for the update method to update everything with delta time. And once we have that, we are drawing all of the elements on the display surface, and before that, we are filling the screen with a black color, so we have some background color. Besides that, we are checking for the player closing the window, but that's pretty simple. And we are updating the entire window so that we're actually drawing something. But that's really quite simple. Nothing really complicated here. actually now look at the classes and let's see what's going on here. And the simplest one is our static obstacle. And in here, we have one init method, and then there we are defining a position, a size, and groups. So all the stuff you could see down here. And well, it's only 4 lines of code. We are using the super.init method to allocate the groups. We are creating an image with the size. We are filling the image with a color, in this case yellow. And then we are creating a rectangle, and the top left of that rectangle is the position. And that's literally it. It's not a complicated object. Now, besides that, we have a moving vertical obstacle and moving horizontal obstacle. And both of those inherit from the static obstacle. So both of these classes inherit from this class here, the one I've just created. And since this one inherits from a sprite, those ones become sprites as well. Except they already have a couple of basic attributes. So let's have a look what they actually do. We have the very same arguments. We have position, size, and groups. And then in the init method, we're passing the same information in there. And this happens both for moving vertical and moving horizontal. As a matter of fact, both of those classes work in basically the same way, except they move either vertical or horizontally. And I guess they have a different color, but that's a small thing. Now, for moving vertical, we are filling the surface with a green color. We are giving it a position, a direction, and a speed. Then for the position, we have a vector 2, and by default, the position is the top left of the rectangle. And this position is what we are going to move. Why we don't move the rectangle by itself is because of delta time, that this position is more precise, which is what we really care about. Now, besides that, we have a direction, which is a vector 2, and then we have a speed, which in this case is 450, but it's basically random. So we essentially create 2 vectors, one for the position, one for the direction, and the speed. That's kind of all we need. Then we have the update method, and in here, ignore this part for now. The important bit happens down here. Essentially, all we do is we get the y part of our position vector, and towards that, we're adding direction.y multiplied by speed multiplied by delta time. So we are essentially moving it in one direction. And after we have done that, we are getting our rect position, and this one actually creates the position of the sprite. And for this one, we're getting position.y and we are rounding it. And that way we are getting the correct position. If this gets complicated, I have explained all of this in a bit more detail in my delta time video. Now, once we have that, we have these couple of lines of code here. And basically, all they're doing is imagine that this right now is the entire distance we want this moving vertical obstacle to move in. And essentially, what this one here does is the top part is 120, so that's 120 up here, and the highest part is 600, so we are down here. And essentially what happens in this top bit here is if the bottom of the rectangle is greater than 600. So if the obstacle is, let's say, down here, and the bottom part is at, let's say, 605. If that is the case, we're moving the bottom of the rectangle to 600. So we're moving this thing up by a tiny bit. Then we are updating the position. And then we are reversing the direction. And that way, once this rectangle is below the bottom part, it's going to start moving up. And then the exact opposite happens on the second if statement, the one down here. Now we are checking if the top part of our rectangle is smaller than 120, so we are up here. And if that is the case, we are moving the rectangle to 120, and we are changing our direction again, so this thing is moving downwards. And that way the sprite is always going to move up and down continuously. And that is literally the entire moving vertical obstacle class. And if you understand this one, moving horizontal obstacle works in exactly the same way, except now we don't change position.y, we change position.x. And that way we're moving in the horizontal axis, not in the vertical anymore. But besides that, this one does pretty much the same thing, except, well, we have different numbers. So those two classes, pretty simple. Now, besides that, we have player and ball. And I guess ball is the easier one of those two because this one doesn't do anything right now. So in here, we only have an init method. We have super under init. Then we have an image and we're filling the image. We're creating a rectangle. And then we have a position, a direction, and a speed. And for now, since we're not updating any of this, this doesn't do anything. But we will work on that in just a bit. Now, finally, we have our player. And this one is getting a touch more complex, although not that much. We again have an image that we're filling with blue. We have a position that is in the middle of the screen, roughly. And we have a movement, we have position, direction, and speed again. So this is identical to all of the other classes. Besides that, we are getting some input. So we are checking if the player presses up or down to move in the vertical direction. And if the player presses neither, we are not moving at all. And if the player is pressing right or left, we're moving left or right. And if the player presses neither of those two, we don't move at all. So this is getting all of the input. And essentially what we do for the input, we check keyboard input and we use that to influence the direction. And now, once we have all of that, we have our update method. And in here, we are first checking for the input. After we have done that, we are normalizing the vector in these two lines. And normalizing a vector basically means that we make sure the length of the vector is always 1. The idea here is that we only move up, we would move by a unit of 1. And if we moved only right, we would also move by a unit of 1. But if we move to the top right, we would have a speed of 1.4. So if we move diagonally, this basically means we would move faster. And these two lines avoid all of that. So all this really does is it makes sure that this 1.4 becomes a 1. Once we have that, we are again updating our position. And this time we are getting just the position and we're adding the direction, the speed, and delta time and multiplying all of them together. And then we are setting the top left of our rectangle to rounded position X and rounded position Y. And that way our player is going to move. So if I run all of this again, we can move the player around and everything works just fine. Cool. So that is a pretty good start. I hope all of that makes sense. So the important question now is how can we add collision mechanics? And for that, we do have to talk about some theory. I'll try to keep it short. And in here, the first important thing you have to understand is that we have a separation between updating our game and drawing all of the elements. So essentially, before we are drawing a frame, we first figure out where all the elements have to be. And this is important because it gives us some leeway to place elements. And for collisions, this matters in particular. So let's think about collisions in the real world. Let's say you throw a ball at any kind of object. Essentially what happens, at some point the ball collides with the outer part of the object and the two don't really intersect with each other because they're both solid. In games, collisions work slightly differently. Essentially what we do in a game, we first check if the two objects are overlapping with each other. So if the ball and the other objects share some space. And if that is the case, we want to move the ball outside of the object. And only once that is done, we are actually drawing the image. So for the player, it looks like the ball didn't actually go inside of the object. But what actually happened was that the ball went inside of the object and we placed it just outside of that object. And that's why we are simulating a collision. And that is the first thing you really have to understand, that we don't check actual collisions and then we are placing one element at the edge of the other element. And to the player, it looks like a collision, but it actually isn't. But now we have a problem. And to really understand this problem, let me give an example. Here we have a ball and an obstacle. And right now they are obviously overlapping. And now imagine you're the computer and you have to figure out where to place this ball. And the problem you now have is you don't actually know where to place this, because this ball could have come from any direction, and you really have to know where the ball came from to place it on the edge, because you don't know on which edge to place it. And if you had the wrong edge, you would just teleport the ball around, which is something that can happen very, very easily and would make your game look very glitchy and might even break it. So you need to understand where the ball came from to place it in the right position after an overlap. Now, to solve this problem, you have a couple of different approaches. And I'm going to talk about two, but there are quite a few more. And there's one thing both already have in common, and that is that we are separating the horizontal and the vertical axes. So what we are going to do, we are first moving an object in the X direction, then we are checking for a collision, and only once we have done that, we are moving the object in the Y direction, and then we are checking for the vertical collisions. And this is already making our math significantly easier because we only have to check for a single axis. And now inside of both of these axes, we have to figure out where the ball came from. And in the first approach, we are checking our direction. So essentially what we are doing, imagine the ball is again overlapping with an obstacle, and the ball came from the left and is moving to the right. If that is the case, you can assume quite safely that the ball is colliding on the left side of the obstacle. And now that you know that, you can place the ball on the left side of that obstacle and you're basically done. And this you can do with all of the other directions as well. And this system is totally fine. It's really easy to implement and it works pretty well. I have actually used it myself for a complex Zelda game. And in there, it worked really well. But there's one downside, and that is that in this system, you cannot check collisions between moving objects. So for example, in my Zelda game, we have Zelda and we have the enemies moving around. But these two objects do not actually collide, so they can totally move on top of each other. But if you had any kind of moving platform or anything moving that can be collided with, this approach would break. And the reason why it breaks is quite simple. Imagine again we have our ball and our obstacle. And now we have our ball moving to the right, and the obstacle this time is moving as well, also to the right, and happens to be overlapping with the ball. Now, for the game's purpose, we know that the ball is moving to the right, so we would assume the collision is happening on the left of the obstacle. But in this case, this is wrong. The collision would happen on the right side of the obstacle. So we would need another kind of system. And this system does work with both static and moving sprites, but it is a tiny bit more complex. Essentially, we are going to check for every single sprite the current position and the position on the previous frame. And essentially what we are going to do is we are checking for each direction if, for example, the right side of a ball is greater or equal than the left side of the obstacle. And on top of that, we are also going to check where each of these sprites were in the previous frame. And now, again with the same example, we have a ball moving to the right and we have an obstacle moving to the right. And the obstacle moves a tiny bit faster. And on the old frame, the obstacle is just to the left of the ball. And then in the current frame, the obstacle is just overlapping with the ball on the left side. If we have this kind of setup, we know that in the previous frame, the obstacle was just to the left of the ball, so we know where the collision is going to happen, on the left side of the ball, or on the right side of the obstacle, whichever one you want to work with. And that way, we don't get confused by different directions, we just check where the object is now and where it was in the last frame. And that is also going to be the system we are going to implement. Now, unfortunately, this is going to be a tiny bit more complex, because for every single sprite class, we have to check the current frame and the previous frame. Although that's, well, one more line of code, it really isn't all that bad. And, well, let's implement all of this and let's see what we get. Here we are back in the code, and for each of these objects, I have to check where they are right now and where they were in the previous frame, which sounds way more complex than it actually is. So let's start with the static obstacle. This one needs one as well, even though it doesn't move. And essentially, all I am going to do, I'm going to give each of my sprites another attribute that I'm going to call self.oldRect. And all I'm going to do here is self.rect.copy. For this one, we are just going to copy this rectangle, and since this one isn't moving, we can just keep it like this. But let me copy this line. We are going to need it a bit more. So this one already done. Now, a slightly more complex one. We have our moving vertical obstacle. In here, we still want to copy the rectangle. But now we have to do something else. That when we are updating this sprite, all the way before we do anything else, I want to get my old rect and copy it. So this is the position where it is right now. And after all of this code is run, this sprite is going to be in a new position. Essentially what this means is that this is the previous frame, and this one down here is going to be the current frame. And well, this is actually all we needed. So now I can minimize this class here and do the same thing to my moving horizontal obstacle. In here, we again are going to need an old rectangle, and we have to do the same thing for the update method. And again, this is pretty much the same thing as we have done with the vertical obstacle. In an actual game, those two could probably be one class. I was just a bit lazy for this setup. But all right, now we have the player, and in here, let's say for the position, I again want my old rectangle and copy it. And then, before I do anything else in the update method, I want to get an old rectangle as well. So again, we have our previous frame and we have our current frame down here. And now let me minimize the player, and we can do the same thing for the ball. We just need the old rectangle. And now, if we run all of this, we literally cannot see any difference, but we can actually visualize what we have just done. Before we are drawing all of the elements, what I want to do is for sprite in all sprites.sprites. And I just want to draw pygame.draw.rect, and this just means we are drawing a rectangle. And then here I want to draw on the screen. I want to draw in a color I haven't used yet. Let's go with orange. And then sprite.oldRect. And let's see what happens now. So now you can see this very faint orange background. And this is the previous frame. Now, because of the frame rate, it is kind of hard to see, but it is definitely there. So this previous frame, very, very small. So at the very least, we know it is working. But now that we have that, we actually have to work with the collisions. And this, let's start with the player. So inside of my player, I want to create another method. And this I called collision. And in here, we need self, and I also want to get a direction. Because remember, we are first going to check the horizontal and then the vertical direction. You could switch this around, it really does not matter. And now, first of all, I need all, let's call it the collision underscore sprites. And this essentially is going to be all of the sprites our player is overlapping with. So let me comment this out. So for example, if I move my player to the obstacle down here, right now they are overlapping. So this yellow rectangle here should be in my collision sprites. And if I were to collide with multiple objects, they should also be in there. Now Pygame has an inbuilt method for that. It is called pygame.sprite.spriteCollide, all in lowercase. But for this to really work, our player has to know where all of the obstacles are. So what I did, when I create a player, we have another parameter that I called obstacles. This is just going to be self.obstacles is going to be obstacles. And these obstacles, let me minimize my player, we get down here when we are initiating the player. Besides putting the player in all sprites, I also want my collision sprites. And the important thing here is that we don't put the player inside of the collision sprites, we just give the collision sprites as an attribute to the player. So the player knows where all of the sprites inside of this group are, and that's all we care about. So I hope that makes sense. All right, so now inside of the player, we need 3 arguments in here. We need a sprite, we need a group, and we need what is called doKill. Now the sprite we want to look at is just self, spelled properly. Then the group we want to look at is self.collision sprites. I think I called it self.obstacles. And for doKill, this should be false because I don't want to delete any of the sprites. And all right, now we can just print and see what we get. So print collision sprites, and then let's put it down here. Self.collision sprites, self.collision. And let's say just test. It doesn't really matter what we put in here for now. So now if we run this, we get an empty list. But if I move over something, we get static obstacle sprite in 2 groups. We get our moving horizontal sprite. And well, we know what each of these sprites are going to be. So this is all we cared about. So this is already telling us if there is a collision or well, an overlap, and with what object the overlap happens. Now what I want to do. I first want to check if collision sprites exist in the first place. So if there's any object inside of that list. And once that is the case, I want to check if my direction is either horizontal. Then I want to do something, let's say pass for now. And if my direction is equal to vertical, then I want to do something else. Let's say pass in here for now. And let's start working on horizontal. Although, again, it really doesn't matter which direction you start with. And what I want to do in both of these is for a sprite in collision sprites. And now the question is the collision on the right, or do we have a collision on the left? So remember, we already know that there's an overlap. And right now, we are just checking if we're moving left or right. So all we have to figure out from the player's perspective is if the collision happens on the right or on the left. And then once we get to the vertical side, we are checking if the collision is on top or at the bottom. So now how can we check if the collision is on the right? And here we need 2 if statements, or well, we need 1 if statements with 2 conditions. The first is self.rect.right is greater or equal than sprite.rect.left. If this one here is our player, so this is our self, and then our sprite rectangle is, let's say, this yellow thing here. Right now, we know there's no collision. And we know that because the right side of the player, so this point here, is, let's say, on position 100. And the left side of the obstacle is at, let's say, position 150. Now, because this position is smaller, we know there's no collision between these two. There couldn't be because the right side of the player is too small to even touch the left side of the obstacle. There literally cannot be any kind of collision. But now, if we have another kind of collision, let's say now our player moved to the right and now looks something like this. The right side of the player is at position, let's say 200, and now this condition here is going to be true because the right side of the player is greater than the left side of the obstacle, and as a consequence we know there's going to be a collision on one of these sides. And let me clean this one up a tiny bit so I have a bit cleaner of a space. So now we have this situation here where we know the right side of the player is greater than the left side of the obstacle. And this means we do have a collision. The problem we have right now is that this situation by itself doesn't help us to understand where the player is supposed to go. So is the player supposed to go to this point here, this point here, this point here, this point here, or any of these other points. We don't know where to put the player because we don't know where it came from. And it might seem obvious to put the player on this side, but that would not be a good way to think about it, because the player might as well come from this direction here. Or if the player moves really fast, it might have even come from this side, and the collision was actually supposed to be here. Remember that when we just check initially, we're just checking for an overlap. So if the player moves very fast, it might even happen that the player jumps over most of the obstacle. So even though the collision is on the right side, initially a player is more on the left. Which is also the reason why you couldn't check something like the center. That's not really reliable. But okay, I hope that makes sense. To fix all of this, we are going to need another statement. That's going to be AND. And what we're going to check in here is self.oldRect.right is smaller or equal than sprite.oldRect.left. And let me actually reopen this one and clean it up a tiny bit. Here again, we are in the starting situation, where again, we are in this situation here. We know there's an overlap. But now what we're also going to check on top of that is this situation here. Let me use a blue color. So this situation here, we are basically checking in the previous frame if the player, for example, was here, where the right side of the player, so this bit here, is smaller or equal than the left side of the obstacle, which in practice means that the player in the previous frame was to the left of this obstacle. So with these two conditions, we know that in the previous frame, the player was to the left of the obstacle, and in the current frame, so this one here, we know the player is colliding. So with these two conditions, we know the player is colliding and did come from the left in the previous frame. So once we have all of that, we can self.rect.right is going to be equal to sprite.rect.left. And don't forget, we also have to set self.pos.x is going to be self.rect.x. So what have we done here? Let me reopen all of this and clean it up a tiny bit again. There's a lot of drawing involved in all of this. These two lines here are going to do. If we again have our situation up here, essentially what we want to do, we want to move this purple rectangle to this position here, where we are moving the right side of the player to the left side of the obstacle. And that way, it looks like the player is colliding with the obstacle and cannot go any further. Or at least that's what it looks like to the player. But in reality, we check for an overlap and then we place the player in a certain position. And then position.x is our actual thing we are moving. So this always has to be in the top left of this rectangle. And this is why we're updating it here as well. And there is one more thing that we have to do. And that happens in the update method here. So this line right now is a problem. Because remember, we first want to move in the horizontal direction, then we want to check the horizontal collisions, then we want to move in the vertical direction, and then we want to check collisions in the vertical direction. So we essentially have to separate this movement here in an X and a Y position. So what that means in practice is ultimately fairly simple. I first want to get my self.pos.x plus equals self.direction.x, multiply this with self.speed, and then multiply this with delta time. And now once we have that, self.rect.x is going to be rounded self.pos.x. And now, once we have done that, I want to check my self.collision. And for now, I just want to do my horizontal collision. And just so we can move around with the player, I also want to do the same thing here for the Y position. So let me copy all of this and let me remove these two lines entirely. So now this should be self.pos.y and direction.y, then rect.y and position.y. And what we're going to do in just a second is self.collision and check for vertical collisions. But this one we don't have right now, so this one doesn't do anything. And well, let's run the code and let's see what we get. So what I could already see, something is happening. So now if I move around with my player, there we have a collision. And right now this only works on the right side, but it does work both with moving and with static objects. The red square right now doesn't have any collisions, so just ignore that one. But you can already see the problem. If I move from any other side but the right side, the collisions don't work. So this we have to implement as well. But the right side by itself works beautifully fine. Cool. So essentially all that means is we have to write 3 more if statements for the left, the top, and the bottom. And I would really recommend for you to try to figure this one out yourself. So try to write the collision mechanic for the left side, the top, and the bottom, and see how far you get. Let me just copy the entire if statement and paste it in here. Now, what we want to check for this one is if the left side of our rectangle is smaller or equal than the right side of the current sprite. So if I'm drawing all of this one out, let me give a bit more space. This one here is going to be our obstacle. And right now, what we want to check is a collision on this side here. And in this if statement right now, we basically want to check if the player is somewhere like here. So if the left side of our player is smaller than the right side of our obstacle. Kind of the opposite what we have done in the first if statement for the right side. And on top of that, we want to check this second if statement. And this one has to check if in the previous frame the left side of the player was further to the right than the right side of the obstacle. So what that means is self.oldRect.left is greater or equal than the old right side of the rectangle. And once we have that, we are good to go. Those 2 lines can stay identical. So let's run the code, and these collisions still work just fine. Now let's try the left side, and they don't work because I made a mistake. Let's have a look. But this is actually really good. So now you can see what happens when you mess up the collisions, that the player just teleports around, which feels pretty bad. Well, kind of funny, but let's see what I did wrong. Like I should tell, this line here has to change, because now we want to change self.rect.left has to be on the sprite.rect.right. And now let's try this again. So now left side still works, and the right side now works as well. And with the static obstacles, this one works as well. And this one works as well. Cool. So with this, we have the left and the right side. Nice. So next up, we have to do the same thing for the vertical direction. And for all of this, let me copy these couple of lines here and let me paste them in there. And now we want to check a collision, let's say on the bottom and a collision on the top. And I guess let's do another round of drawing for the bottom part. I again have my obstacle. And what I now want to check is if my player did something like this, where the bottom of my player is greater than the top of the obstacle. And for that, I need self.rect.bottom is greater or equal than sprite.rect.top. So now we know there's some kind of collision, at least on this axis. And now what I want to check if in the previous frame, the player was above the obstacle. So if oldRect.bottom was smaller or equal, this one can stay, then oldRect.top. And now once we have this if statement, and this is true, I want to check my rect.bottom to the top of the other rectangle. And now this position x has to be position.y. And this is basically all we needed. Now, for the final if statement, let's do this a bit faster. We want to check if the top of my rectangle is smaller or equal than the bottom of the obstacle, and if the old top part of the player was greater, so below, than the bottom of the obstacle. And if that is the case, I want to set the top of the player to the bottom of the obstacle. And then again, we want to check position and rect.y. And with that, let me fix this typo. With that, we should be done. Let's check this. Now our player can't move inside of this purple rectangle anymore because we are being moved along with it. I can't also move inside of any of these objects here. And let's check the green rectangle, and this one works perfectly fine as well. Cool. So let's try the top side. And yeah, this is working really nicely. So with that, we have a basic collision mechanic. So this one is working really, really nicely. And I guess now that we have that, let's minimize the player. Let's remove some white space. And now we can do the same thing for the ball. And this could be a pretty good exercise for you. So from the stuff you have just learned, try to make the ball bounce around the game window and make it collide with the player, with the obstacles, both the static and the moving ones. And this should take you some time, but try to implement this one. First of all, we need to create an update method that needs self and delta time. And in here, I am going to steal quite a bit from the player because, well, it doesn't make sense. So we can take all of this, actually all of this from the player. So let's copy all of this into our new update method. And the one thing I don't need for this one is the input because the ball doesn't have any input. We essentially just give it a starting vector and then change the direction whenever it collides with anything. And now we are going to need two more methods. The first one is going to be collision. And this one needs self and direction. Let's copy this one straight from the player again, because we are going to reuse quite a bit. So I'm going to copy all of this here and paste it inside of the collision method. So quite a long method, but I hope you understand it. Now we do have a problem. And let me go to the init method and let me minimize the collision method. This ball right now doesn't know wherever of the obstacle or where the player is. So we have to tell it that. And for that, I created two new parameters when we initiate this class, obstacles and player. And let me add them right at the bottom. So we have self.obstacles is going to be obstacles and self.player is going to be player. And now when we are creating this ball, I first want to insert my collision sprites. And besides that, I also need the player. But right now I don't have access to the player, so I'm going to place this in a separate variable. And then this variable I'm going to place inside of the ball. So now our ball is going to know, let me minimize the player, we don't need it anymore. So now our ball is going to know where the obstacles are and where the player is. And now let's actually run this and let's see what happens. So now the ball is colliding, but well, you can see two problems actually. The first one is that when the ball collided here with this object, it didn't change the direction. So it just went like this, then shimmied along the side and then went down. And the second problem is that it just left the screen, so it went down here. So these two things we have to work on. And both of these things aren't terribly complicated. I guess let's start on changing the direction. Essentially, what we want to do. If our ball collides on the horizontal axis, we want to self.direction.x and multiply equal this with -1. So at a +1, we become a -1. So this way, I have to copy this to both of these. We would change our direction if the ball is colliding in this direction. And we have to do the same thing for the vertical axis, except now it's direction.y. And now let's try this again. And this is working better. But we do have to work on the window itself, and that one shouldn't be too hard. As a matter of fact, if you understand this logic here, figuring out the window logic shouldn't be too hard. But, well, let's do it together. So I want another method, and I call this one the window collision. And here we need self, and I also want to have a direction. And basically what I want to do, after we have run all of this, I also want self.window collision, and this one should also be horizontal. And then I can copy all of this and do the same thing for the vertical collision. So we essentially have two different kinds of collision, except the window collision is going to be fairly simple. Basically, all we are going to do in here is if the direction is equal to horizontal, and if that is the case, if self.rect.left is smaller than 0, which means that our ball is moving to the left side of the window. If that is the case, I want to set self.rect.left to 0. Then I have to update the position as well. So self.pos.x is going to be self.rect.x. And finally, self.direction.x. I want to again multiply equal with -1. So we are changing our direction. And now we just have to do the same thing for the right side of the window. So rect.right. And in my case, my window is 1280 pixels wide. Although in a real game, you would store this variable somewhere separately so you can access it a bit more easily and the game is a bit more flexible. But in my case, I don't care about that. Now, if that is the case, self.rect.right should also be 1280. And this one is still fine. So now let's try this one. And something went weird. And the problem here is self.rect.right should be greater than 1280. Now let's try this. So now we have a collision with the right side, but not with the top. So at least something is working. And well, basically all we have to do is copy all of this here and change the direction to vertical. And now we want to check if rect.top is smaller than 0. And if that is the case, we want to set the top to 0, and then position.y is going to be rect.y, and direction.y we multiplied with -1, so we are reversing the direction. And for the final one, self.rect.bottom is greater than 720. And if that one is the case, then self.rect.bottom is going to be equal to 720. And finally, we have to change all of the x's to a y. And now let's try all of this again. This one is working, this one is working, this one is working as well. We don't have player collisions yet, that's going to come in a second. But besides that, things are looking pretty good. Okay, cool. Now, the final thing we have to address is the collision between our player and the ball. And this is going to happen inside of collisions. Let me minimize all of the other methods so it's a bit easier to see what's going on. The problem we have right now, that our collision sprites just checks for the obstacles. So we don't check for any collision with the player. And well, we just have to add 2 more lines here to fix that. And basically what I want to check, if self.rect.collide rect. So if the current rectangle of the ball is colliding with self.player.rect. And this is a very simple, I should spell it correctly, this is a very simple rect collision method that just checks if 2 rectangles are overlapping. That's all we're trying to do here. So this is basically telling us if the rectangle of the ball is overlapping with the rectangle of the player. And if that one is the case, we want to collision sprites dot append self dot player. And now let's try this again. And now let's try to get it. And yeah, this is working just fine. Hope I can get the ball again. The ball is moving quite fast, so it's a bit difficult to get it. Okay. Well, I hope you get the idea. There we go. There, yeah. So this seems to be working just fine. Cool. And well, with that, we are pretty much done. Now, before I finish this video, there are two, I wouldn't call it bugs, but two things we don't really cover in this kind of logic. And to fix this, we would need quite a bit more code. So I'm kind of going to ignore them. But let me visualize what the problem here is right now. Let's say I'm going to move my player exactly in this, wait a second, in this position here. Now you can see that we get kind of a bug that the player is pushed through the yellow rectangle. And the reason for that is that this green rectangle is just pushing the player, and that is overwriting this collision here. And the other problem we have here is if our ball is colliding with any of the moving obstacles. It's kind of hard to see right now. I'm probably going to add some kind of video to explain it a bit better, because it only happens sometimes. The basic problem is if the ball is being pushed down by another moving obstacle. So if, for example, the ball is being pushed down, we get kind of a random direction. Because every time these two collide, the vertical or the horizontal direction of the ball is being reversed. So if they collide once on one frame, we get one collision and then it changes direction. But if they collide again on the next frame, we get the same thing again. So the direction changes again. And this happens probably hundreds of times if the ball is being pushed down or up or left or right. And as a consequence, we get kind of a random direction afterwards. And you could add a lot more code to account for these cases. Although another thing you could be doing is design your levels in such a way that this problem doesn't even come about. So for example, if you have moving platforms in a game, make sure these platforms can never squash the player between themselves and another kind of object. Or if you have something bouncing around, make sure you work with the directions to address all of this, that there couldn't be a bug. So just keep these things in mind, but well, I hope this video was helpful and I will see you around.